Hi and welcome. Today we're going to be solving a couple of problems, and one of them is presented to you right now. And let's read the problem. And it states as a car starts to accelerate at a constant rate of 0.8 meters per second squared. It covers 400 meters while accelerating in the next 20 seconds. What was the speed of the car when it started to accelerate? Again, let me repeat. What was the speed of the car when it started to accelerate? So from the word what was the speed of the car means it is from the past. Okay? What was the speed when it started? So let me just mention this. Started to accelerate. So it means that it started at one point and then it accelerates and then up at this point with a velocity. And this is our final velocity, and this is our initial velocity. So therefore, we are supposed to be solving for the initial velocity. But what are some of the additional informations that were provided to us? 400 meters. So 400 meters means it is our displacement, which is your delta x in this case. Constant rate of 0.8 meters per second square. So that means that this is your acceleration, which is 0.8 meters per second square. So the square of the time. So we are supposed to be solving for our, not delta x, but we're solving for our initial velocity, or v naught. What additional information do we need here, or it's provided to us? It says something about 20 seconds. So 20 seconds, we're knowing that 20 seconds represents time. So that is 20 seconds. So 20 seconds. So by looking at the different equation that we are provided with, so again, we have to solve for V naught. First equation that we have from our list of equation, let me just write it at this section. First equation is V minus V naught plus acceleration times time. Maybe I can use that equation. Right? Maybe I do have some informations. Second equation that I do have is x equals x naught plus v naught times t plus 1/2 a t squared. Okay. And then third equation that I have right here is my v naught. The v squared equals v naught squared plus 2a delta x. So those are the three equations that I know that I can use. If I analyze the first equation, which is v naught plus at, I'm not provided with v, but I can solve for v. But why do I have to do the burden of solving for additional information that I might not even need to solve first? So let's take a look at a different equation. V squared plus v plus 2ax. I still need to solve for v, which I don't want to. So there's another equation, which is your second equation that I skip because of a purpose. I want to stay away from the second equation if possible because that's a quadratic equation. However, sometimes using the second equation is much better rather than doing two steps of an equation. So let's take a look at this. X naught plus v naught plus times t plus 1/2 at squared. So there's no mention of v, or the final velocity. So maybe I can use number 2. Maybe I'm right, maybe I'm wrong. So let's take a look by applying it. So let me just transfer or rewrite my second equation here in the bottom. So that's x equals x naught plus v naught t plus 1/2 a t squared. Okay, so I noticed that there's x and x naught, and they're not in the same side of the equation, maybe it will be better if I combine them in the same side of the equation. So I'm going to move my x naught to the other side. So that will give me x minus x naught. X minus x naught is equivalent to a change in position. And if I look at my problem, if I look at what's stated in my problem, I do know that there is a displacement or change in position, which is 400 meters. So I can just rewrite x minus x naught as delta x, which is my displacement, equivalent to v naught multiplied by t plus 1/2 a t squared. By looking at our equation, I would say manipulated equation, and see if we have all the information we need to solve for a. Since we know that this equation contains a, it is possible to use this equation to solve for a. I have my delta x, which is my displacement, which is 400 meters. I have my v naught. I can solve for v naught. I do have my acceleration. So did I mention solving for acceleration? We're not solving for acceleration, but rather we're solving for v naught. Acceleration is provided, which is 0.8 meters per second squared, and time is also provided at 20 seconds. So all we have to do is just plug in the values, which will give us 400 meters v naught multiplied by time, which is 20 seconds, plus 1/2 multiplied by the acceleration, which is 0.8 meters per second square, multiplied by the square of the time, which is 20 second square. Okay, so by just copying this number, which is 400 meters, velocity 20 times s plus, so if I add all these numbers right here, so if I add all the numbers, let me just calculate and see. So that will give us 0.8 times 20 square divided by 2, which will give us 8. Okay, so 8, but let me just take a look at this. Oh, it's not even 8 because it's 20 squared. Okay, that was my mistake. So let me just write it down. 1/2 0.8 meters per second squared. So that will give us 20. So that is 20 square is 400. But instead of meters per second, so that will give us second square. Now I can cancel my square. Okay, and cancel this. So if I am going to rewrite this, meters v naught 20 seconds, and this will give me plus 400 times 0.8 divided by 2. So this will give us 160 meters. So I can move it to the other side of the equation. So if I move it to the other side of the equation, this will give us 400 meters. So my units are consistent. So I cannot subtract 160 if it's not in meters also. Since my units are the same, so I can subtract, I can proceed with the operation. So that is 400 minus 160 meters. And that is equivalent to v naught multiplied by 20 seconds. So that's your 20 seconds. So v, so if I can simplify it further, so I can write it here. So that will give us v naught, which is right here, is equivalent to whatever the product or whatever the difference is. 400 minus 160 will give us 240 meters divided by 20 seconds. So this will we can arrive with an answer that is 240 divided by 20. So that will give us 12 meters per second. So this means that in the beginning, the velocity of the object or the particle or the car itself that's mentioned in the problem is 12 meters per second heading to the right direction. So in the next video, you will see another problem solving of a different problem to help you guide with some of the questions that you are going to finish. See you in the next video.